Can you see that, Tanya? And if you guys have questions as you go, feel free to pop them into the chat. Tanya will hopefully answer them or relay them to me because I can't see any of you anymore. So R is magic. R is a fabulous tool that will make all of your wildest dreams come true and make you into a way better scientist, period. R is basically an alternative to things like JUMP that are like the click and point version of statistics and plotting. There's so many benefits of R that hopefully will become clear as we go on. Our goal of today is just to get you started. So if you've never opened R before, awesome. If you've opened R and you're rusty, awesome. I want to try to get you started, talk about sort of the terminology and the tools that are involved in it to hopefully decrease the slope of the learning curve. You've probably heard from people that the learning curve is very steep and it's totally terrifying, and I agree. But hopefully with the tools that we'll give you today and the sort of resources that we'll give you and that we can be as you go through learning R, that learning curve will be a little bit less steep. So if you open RStudio, this is what it will look like. Basically, as Matt very eloquently put in the email, R is very clunky in and of itself. And so RStudio basically is this beautiful user interface that I think almost everybody that I know uses. And so you have to have both R and RStudio downloaded on your computer. It should look something like this. Tanya took this screenshot earlier today of her crazy modeling stuff, but basically it's sort of a 4-panel situation. So the bottom left panel is the console. That's where the magic happens, where code actually gets run. We mostly don't work directly on the console. We work in the top left corner, which is called the source code. It's basically like your draft code. So inevitably when you're coding, you'll make mistakes, you'll do something really stupid, it'll be completely inefficient, and then you'll go back, revisit it, make it better. And so if you actually work in your source code, then you can make changes to it as you go. Whereas once you put stuff in the console, it basically gets swallowed up and disorganized and kind of goes away. So the code that I've put in the Google Drive folder, you would just open in RStudio. It would populate that sort of top left corner of your screen. And then you would work from that code. And basically, I'll show you later, but the code will go from the source code into the console. The top right is what's called the environment. That's where variables go. So if you say like, I want to make something called T from this data set that I'm going to upload, then T will actually show up in that top right corner in your environment. And you can see what T is, what it has, what it looks like, etc. And then the bottom right is where all the fun stuff is. That's where your plots will pop up when you make them. It's where the files are in your working directory, which I'll talk about in a second. You can see, you know, the packages you've downloaded. You can get help. That's probably the thing I use the most because it's just a continual learning experience. And then you can view different data sets and stuff like that. So you'll see once the PowerPoint is done and I open RStudio that it will be a blank slate with these 4 sort of panels. So how do you actually run code? Move you guys out of my way. You can do it directly in your console. So if I go back one slide, in this console in the bottom left corner, you see this little like greater than symbol on the bottom. That's the little caret, indicates that that the console is awaiting your instructions. So if you type, for example, 2 plus 2 into that console and you press enter, R will spit out the number 4. At the very least, R is just a glorified calculator. I use it for that sort of thing, like my taxes all the time. If you mess up and you, for example, enter 2 plus and then press enter, it's basically an incomplete statement, right? And so R will then be waiting for you to do something else. That's what this plus sign means. And so to fix that, you can either finish the statement. So you could, for example, type 2 and then press enter and it'll spit out 4. Or you can press escape and just get a fresh start. I see a lot of beginners sort of get stuck in that loop where they accidentally put something in that's incomplete and then they can't figure out how to get out of that. And then once you get to more advanced code, sometimes it takes a long time. And if there's just a space instead of that little caret, it means the R is actively working. If you accidentally like wrote code that doesn't work and it's just like an endless loop and you're stuck, you can always press the stop button and it'll just stop what it's doing and give you that little ready caret and you can start over again. Like I said before, we often don't work directly in the console. We actually work in the source code, which is that top left panel where that sort of draft is. And And so what you can do to actually run the code that's in your source code little document thing is you can press the run button. That's the easiest way to do it. Or you can use your keyboard shortcut. So on a PC, it's Control Enter. On a Mac, I think it's Command Return. Please correct me if I'm wrong. I don't have a Mac. So any of those things should work. So for example, going back to the source code here, if I wanted to run like line 15, I would just put my cursor anywhere on this line, and then I could press this run code button on the top right, or use my keyboard shortcuts of Control Enter on PC or Command, I think, R on a Mac, or Command Return. And that will basically it'll copy the code from your source code into the console and actually execute that code. It'll run. So if you put 2 + 2 in there, you run it, it'll move it down to the source or to the console and actually spit out the number 4. Okay. I don't want to go too into types of data, but this is where a lot of people get hung up. Data in R are of a certain class. They can be numeric, like non-integers, so like 1.1, 6.258, or they can be integers, like these whole numbers. They can be categories, they can be a text string, they can be logical, and how you actually check what type of data you have in R is in that environment, the top right panel, it actually says, so for example, we're gonna upload some data later that are gonna be called D, and you can actually see it says CHR up here under site. So site is a character, and the site's names are like A, B, and C or whatever. Mussels, snails, and barnacles are all integers because you can't have a half of a mussel, right? So all of the counts of the mussel abundances are whole numbers. The reason this is important is because R assigns a type or a class to any data that you put into it, and certain types of analyses only work with certain types of data. So for example, if you're trying to do a bar plot, but you're doing it with 2 numeric variables, that's not going to work, right? You should have used a scatter plot, and so it'll mess you up if you don't have the correct type of data for that job. Okay, so the basic types of sort of structures that you'll work with are vectors, matrices, and data frames, and I'll go through them one by one. So a vector is basically a one-dimensional string of values. So if you were to type into your console 1:10, the colon just means like through in R. So this is like 1 through 10. It'll spit out literally the numbers 1 through 10. This is a vector. It's just like one single chunk, one little string of numbers. A matrix is basically a 2-dimensional version of that. So a matrix, like this matrix in particular, don't worry about the code that I used to make it, but basically it's a 3-row by 3-column grid of values. This is mostly what you're going to work with, either a matrix or a data frame. A data frame is the same thing as a matrix. The difference is that you can have mixed types of data. So you could have, for example, characters and numbers in the same like table. If you look at a matrix, it's basically just 3 vectors stacked on top of each other, right? And so you can subset different parts of a matrix. That's probably one of the more common things that you'll do, and we'll get into that a little bit more later. But the basic thing here is just a vector is a 1-dimensional string, a matrix is a 2-dimensional grid, and then there's data frames.
You can also have just a single value too.
That's also true. Yeah.
Mathematically, it's called a scalar. So anyway.
Thank you. Okay, so functions are something that are a little bit more complicated, but again, something you're going to use a lot. It's really no different than like the functions you learned in algebra, like f of x equals 2x plus 1. There's a name of the function. So here a function is called f. There's arguments or parameters that are put into that function. And then there's a definition, which is used to calculate the output. So for example, 2x plus 1 is a function called f. It requires an input called x. And so if you put 3 into this function, it'll spit out 7, right? 2 times 3 is 6, plus 1 is 7. So that's what you see here. F of 3 will equal 7. You can make your own functions. There's also a ton of built-in functions in R that do different things. So for example, You can take an average of a bunch of numbers using the existing function called mean. So you just do mean, and then you put in some numbers, and then it'll spit out the average. They can also have lots of inputs and arguments, so they can do more complicated algebra than you or I could in just a crazy small amount of time. And then you'll probably hear us talk about packages. Don't stress too much about them, but packages are basically collections of functions. And so people have gone through and done a ton of work for you, and you can just download these magical packages, and they have really cool functions that do awesome things. So that's one of the things I found was hardest when I learned R, was that I didn't really know what existed and what didn't. And so I ended up making a bunch of my own functions that I didn't need to. So if in doubt, Google it, Google like R, and then whatever you're trying to do. And oftentimes some sort of exchange with people, some sort of website will point you to a package or a function that's super handy. There are packages that are built in. There are other packages you can install and load, and we'll show you those as well a little bit later. I put this up here just to show you an example of sort of common functions that are used. I mean, you can just look through them. So like ABS, that calculates the absolute value. So if I was to do the absolute value of -1, R would spit out the number 1. What else? Length of X. So if you put in like a vector of 10 numbers and ask R to give you the length, it'll tell you that there are 10 values in that vector. You can do things like sequence. So like the sequence call makes a sequence from 1 to 10 by 0.4. That's super handy if you want to make whatever vector of numbers with equal spacing. You can sort stuff, you can order stuff. It can tell you what time it is. You can look where you're actually working. There's all sorts of things that are just built in. And I definitely recommend just kind of looking through this to not familiarize yourself with all of the options, but just to see what's possible and what might exist as you go through your own data sets and have your own unique challenges. And then there's subsetting. I guess I'm going to say this for everything, but subsetting is one of the things you're going to do a lot in R. So you saw in all of these functions that I showed you, these sort of round brackets, these parentheses, those are part of functions. Square brackets are used for subsetting. So those are like the square brackets on the sort of right side of your keyboard. Let's say you have that vector of the numbers 1 through 10, and it's called T. So every time you type T into R, it'll spit out 1 through 10. Let's say you want to see what the fourth value is in that vector. You would do this little call here, T square bracket 4 end square bracket. And that would print the fourth value of that vector. It's super handy, for example, if you want to, like, I don't know, pull out a random, like a specific number in a very long vector without scrolling all the way through it. So in Excel, you'd like scroll to the 12,000th row. In R, you can just write that call and it's super quick. Because matrices are 2 dimensions, you have to give it 2 numbers to subset. The first number is the row, and the second number is the column. So what this little line here does is it takes T, so let's say there's a matrix T, and it'll give you the value that's in the third row and the second column. The way that I remember this is that the RC lab, which is the Ramundi Carr lab, it's always in that order. It's always P and then Mark, R and then C. And so in this call, it's always rows and then columns. That'll be important later. And then the other thing you can do is give you, for example, all rows of a single column. So if you want all rows of the second column, you just don't specify a specific row. You leave it blank, and then you give the second column. And you could do the opposite if you wanted to, for example, extract all columns of a particular row. You would do like T square bracket 2 comma, and that would be the second row and all the columns. And with all of this stuff, just remember that whatever you type into the console or whatever you type into the source code and run, it'll just print out the answer. It won't actually save the answer unless you tell it to. So if you just put T square bracket 4, it'll output that value, but it won't save it as anything. If you want to save it as something, let's say you want to save it as a new variable called t sub, you would have to say t sub equals t square bracket 4. And then when you then have code that refers to t sub, it'll be that particular value. Does that make sense? The other interesting thing about R is you can use an equal sign. You can also use a less than sign and a dash. These are the same thing. It's a little bit complicated why they're different, but basically the less than dash will work for more things than the equal sign. So you can use either of them. I'll just leave it at that. Just keep that in mind. Okay, so just like best practice stuff. It's really good to keep track of what you're doing and to annotate it. When I say annotate, I mean like talk to your future self about the code you're writing and tell yourself what it's doing and why it's important. I can't tell you how many times I've gone back to code like 4 years after writing it and just like wanted to bang my head against the wall because I had no idea, like it was inefficient and old and it didn't work and I had no idea what I was trying to do. So the best way to do that is to use a hashtag. A hashtag basically denotes a comment. So any text that's after that hashtag, it's just a comment. It's not actually code that's run in the console.
It's not a hashtag, it's a pound sign.
Pound sign. Millennial.
That's a generational thing.
Oh, busting my millennial chops, Tanya. It is a pound sign. Those used to be on landlines. Yeah, so those are super handy. So you'll see in the code that we're going to use, like I usually make chunks of code. Like I'll make a chunk that says like, you know, read in data, and I'll make a chunk that says do descriptive calculations, and hashtags, pound signs are, I have to rewire my brain, are a really good way to do that. Spaces are not allowed in variable names. So if you want to make a variable name, instead of using t, which is like the simple example, let's say you want to make a variable called variable name, you can't put a space in it. You have to use variable dot name or variable underscore name, or you can use capital letters, capital V, capital N for variable name. That's sort of personal preference. Just keep in mind that R is case sensitive. So if you use capitals, you're going to have to remember where you use the capitals. And if you use capitals sometimes and don't use capitals other times, R will get confused and you will be miserable. So I would like decide today you're going to be a period person or you're going to be an underscored person, and just try to be as consistent as humanly possible. I just said that. Dollar signs select particular columns from data frames. So if you have a data frame with 5 columns and one of the columns is named temperature and you want to just like look at the temperature data, you would do data frame name $ temperature, and that would pull out just the data in that column called temperature and spit it out for you. The last thing, this is a little difficult to describe without actually showing you, but when you're in the console, you can use the up arrow to scroll through all the previous lines of code that you've run. So like if you write like a, you know, this crazy super long line of code and you made one mistake, just press the up arrow and it'll like re-put that same chunk of code in the console, and then you can just change the one thing you screwed up. And that way you don't have to retype everything. It's super handy. Tanya, anything else? Tabbing?
Yeah, I mean, that's easier to demonstrate.
Yeah, I think so.
Itself.
Logical operators are something that you'll use more a little bit later, I think. But logical operators basically check whether something is true. So like we've told you that one equal sign will set something equal to something. So t equals 2 takes 2 and sets it as t. If you do 2 equal signs in a row, it checks whether something is true. So if I do like t equals 4, and t is actually equal to 2, it'll say false. It'll tell me that t is not equal to 4, it's actually equal to 2. And so you use that sort of thing a lot in if statements. So I can say like, you know, if this thing is true, then do this to this code, otherwise do something else. Those are the sorts of sentences that you sort of start to write, or the syntax that you start to write when you're doing some more complicated stuff. But it's just good to keep in mind what types of logical operators exist. So in addition to equal to, which is the two equal signs, you can do exclamation point equal, which says not equal to. You can do less than, greater than, less than or equal to. I mean, you can read those. And those just become super, super handy. So let's say like you have a data set that includes, the abundance of seals that you counted at 3 locations and on 2 dates. And let's say you just want to subset the data for a single date and for a single site, then you can use the existing function subset, and you can just subset the data for a site and a year using these logical operators. Again, everything will make more sense when we actually get into R, but hopefully that gives you sort of a foundation with which to move forward. I think this is the last slide. I just wanted to say that R is hard and it's complicated, and for a lot of people it's not very intuitive, and that's okay. You're on the right track, and you have a lot of people around you who work in R a lot and who've gone through the same struggle with you do and know that it's a struggle. So use us, like email me if you have questions. I'm always happy to help people with code. Your peers in your cohort, if you're a graduate student or an undergrad, super good resource. Also Google, if you Google like a specific R error, you can just copy and paste it into Google, and oftentimes people will have done the same thing as you and they can help you fix it. Or if you want to figure out something like, changing the y-axis of an R plot, just paste that into Google, and hopefully Google will help you. That's it for the PowerPoint. So we'll move into R. Do we need to pause for some question time? Seeing a lot of chat things.
Yeah, so some questions about spaces in data. So I guess to clarify, so spaces aren't allowed in the column name, like the names of the columns. If you happen to have like character data that has spaces in it, that's okay, but just not the headings of the columns. If you upload a data set that has spaces in it, R is going to substitute periods for the spaces, which is fine, but it sometimes ends up making really weird variable names. So often it's good when before you upload your data, to just look at how it's formatted, and then like change the column names to get rid of the spaces and make them like more like shorter and easier to look at when you do upload it. So that's something you'll want to think about doing.
Yeah, like if you have like units, I often see units in data sets that have like, -1 symbols and parentheses in your Excel spreadsheet names. I just would get rid of that and just keep it very simple if you can. Unless
yeah, the special characters along with the spaces will get kind of messed up. So it's nice just to make like simple titles for your variables with like minimal frills.
Yeah. Any other questions before we move on? Awesome. That's probably totally overwhelming, but that is okay. I promise it'll make a lot more sense when we actually move into R. So I'm going to screen share our studio. Perfect. Is that big enough, the text? You guys see that okay?
I can see it fine, but.
Okay.
That looks okay to me.
Okay, perfect. I made it giant and also changed the order of the panels around, so this may be a little fumbly. Okay, I also made it blue. The white hurts my eyes, so if you want to change yours, you just go to Tools, Global Options, and then you can change all sorts of stuff about the appearance, like the colors and the size and stuff like that. It's a very good way to procrastinate. Okay, so this code is, like I said, in the Google Drive folder. It's not that long. I guess it's kind of long. I commented a lot of stuff to try to help you understand it, and we'll basically just go through line by line and just see what we can get through. I think, it's probably best for you guys to just look at my screen as we go now, but if you do have the time after we hang up and you can download the code and go through it yourself line by line, I think that's probably one of the best ways to learn. So we talked about packages. I have a couple packages in this code that require installing new packages that aren't provided in base R, and also doing what's library is the function. It basically like loads the package after you've installed it. So the first time you run this code, you will have to run all of these lines, and subsequent times once you've installed the packages, you just run the library call. But anyway, details. So you remember this bottom part is the console. So for example, if I was just to type 2 + 2 and press enter, it'll spit out the number 4. If I type 2 plus, press enter, you remember it's that plus sign. It's like waiting for me to do something. So I'm just going to hit escape and just get out of that. And then we're back to square one. To actually move code, to run code that's in my source, let's say, for example, I want to run lines 8 through 10. I can highlight those, and then I can press Control Enter. And you see that it's basically moving them down here now. Those have all gone through, they've all run, so that's awesome. Can't actually see the run button, here we go. But the other alternative is like if I want to run line 15, I can highlight it and then press the run button up here. That's a little bit more clunky, but to each their own. So this line 15 basically says, I want to take the numbers 1 through 10, and I want to set them as A. So I already ran that line, but I'll run it again for fun. So that line you can see in the console at the bottom ran. And if I type A, capital A, into the console and press enter, it'll spit out the numbers 1 through 10, which is exactly what I wanted. You can also see them in the global environment up at the top right. And that'll basically show you the same thing. It'll also show you the data type, which is an integer. Okay, easy enough. Line 16 is a different way to create a vector. It's using the letter C. C stands for concatenate, which basically is a fancy way of saying stick stuff together. So if you wanted to make a variable A that had the numbers 1, 1, 3, 5, and 10, you would use this line of code. So set A equal to a set of numbers that's all concatenated together. And if you run that line of code, now look up in our environment, you'll see that A is now exactly what I just wanted, 1, 1, 3, 5, and 10. If you set, so like lines 15 and 16, set 2 different things as A, that means that line 16 is basically going to overwrite line 15. So just be careful when you set something to the name of a variable that already exists. Okay, and I already printed that out. So right now, if I type the letter A into the bottom left into the console and press enter, I can just be sure that A is equal to a vector of numbers 1, 1, 3, 5, and 10. Okay. So I told you about the functions that already exist in R. These are some of the ones that I use most often. So like sum of A will just give you the sum of all the numbers, which here is equal to 20. Like I said before, if you just type in sum of A, it won't actually save the output. You have to do this. You have to say, I want to make a new variable called asum, and I want to set it equal to the sum of A. So if I highlight that row and run it, you'll see now there's a second, whoa, what just happened? My computer's freaking out apparently. You'll see that there's a second value now in the environment that's equal to 20, and it's called asum. Other functions that exist are length. Length shows you how long it is. So because there's 5 numbers, it'll spit out the number 5. You can take the mean of A. I'll show you that it's 4. You can do standard deviation. You can do max. You can do min. So it's up to you to decide what's important. Summary is kind of a shortcut because it actually will give you the minimum, some of the quartiles, the median, the mean, and the max. So usually when I put data into R, that's one of the first things that I do is just to make sure that the data are what I think they are and that there's not a bunch of like missing values or like weird negative values or like infinity values that will screw up the downstream code later. Okay, so once you have some variables in your environment, you can do stuff to them. You can manipulate them by like adding 5, for example. So if I run line 31, it'll add 5 to all the values in the vector A. So it just literally adds 5 to all the numbers. You can also do things like multiply by 5. You can divide by 5. This becomes really handy if, for example, you want to, like if you're measuring, I don't know, speeds, like velocities in meters per second, and I don't know, you want to like change the units, then you would divide it by a certain number, and that would actually just scale the whole variable, which is really handy. Other random fun things. So remember, if you forgot what A is, you can always type A into the console and check what it is. If you want to see which unique values are in that vector, you can run line 36, which says unique of A. And that'll tell you, like, because there's two, the number 1 is duplicated, so it'll only show you one of the number 1, one of the number 3, one of the number 5, one of the number 10. Again, this is a really good way to check data. So if you should only have one, value per vector or whatever, you can just double check that that's true. Rev is a built-in function that reverses everything. So if I run that, it just literally goes backwards, which can be handy for random stuff. You'll be surprised. Sequence I already talked about creates a new vector. You specify the min, the max, and the spacing between the numbers. So if I run line 38, then it runs from 1 to 100 by 1. So you can see this now exists. However, because I didn't actually set it as something, it's not going to actually save that set of values, that vector. So for example, if I wanted to make something called R and set all of this equal to R, then I could run that, and then R would actually be added to my environment, and I'd be able to manipulate it. So if I wanted to do R times 0.1, then I could see what those values are. So you can imagine how this is just super handy for doing quick calculations or whatever, something that would take a lot of columns in Excel and would be slow. Imagine, my SEAL diving data records every 4 seconds for 7 months. And so I'm dealing with spreadsheets that I can't possibly open in Excel. And so with this sort of tool, I can calculate the average diving depth in a millisecond, which is very, very nice. You can also make random numbers. This is more common in Tanya's type of work, crazy simulation modeling cool stuff that I don't tend to do, but you can, for example, make a variable of random numbers. rnorm is basically a function that makes a set of normally distributed values. Here I specify that I want 100 values with a mean of 0 and a standard deviation of 1. And so if I type rand just to check what it is, you can see it's given me 100 values with that mean and standard deviation. So let's just check to make sure that it's right. So in the console in the bottom left, if I type mean and I do mean of rand and press enter, it'll show me that the mean is very close to 0, which follows what I specified. And if I wanted to do the standard deviation of rand, I could also check that that is as close to 0.1 as it can be. And so you can see how you use those functions in a really nice way. You can also check the length, for example, to be sure that it's actually 100 variables. The beauty of R is that it doesn't make mistakes, but it never hurts to check that you didn't make a mistake in the code that you told it to run. Okay, so that's how you basically get numbers into R easily and how you manipulate them. Oftentimes, aside from using summary or mean or max or whatever to check that the values are what you think they are, I often plot values just to make sure that I did what I intended to do. I know that Matt's going to have a whole lesson on plotting in R, and that's going to be fabulous. I'm just going to give you the most simple tools I can to be able to sort of check that your data are what you think they are. I won't say too much about this, but basically there's 2 schools of people in this world. One that uses base R, which is the stuff that comes with the basic program, and ggplot, which is a package that makes really pretty graphics. I'm going to show you both. I think that Matt's going to use ggplot. A lot of people use ggplot nowadays. It's kind of a personal preference thing. So whenever in the code that follows, I think there's 3 examples, I put in base R above the ones that are base, and then I put in ggplot in the ways that are ggplot. Same data, same basic outcome of a graph, but very different ways of like controlling what the plot looks like. So we have this thing called RAND. It's 100 numbers with mean of about 1, standard deviation of about 0.1, sorry, mean of 0, standard deviation of about 0.1. Let's say we just wanted to see what the distribution of the numbers looks like. Line 44 is basically a histogram. So if I run that, you'll see that a plot will pop up down here. It's a histogram of those numbers. So you can kind of see what the mean is, and you can kind of see what the standard deviation is. This is the base way to do that, just using hist. In ggplot, the call is a little bit more complicated, but it's also a lot prettier. So you can see it's the same data, it looks the same, just slightly different. You can, of course, change things like, Matt will go over this, but if you want to change the fill to red, it's really easy to be able to do that, or to make custom colors, or to make them transparent, or whatever. You can see how these start to become really beautiful. I'll go through the syntax a little bit later. So we talked about indexing a little bit. I told you that, let's say we have A, which I'll check in the console is 1, 1, 3, 5, and 10. Let's say we wanted to pull out the second value of A, which we can see here is 1. So you would highlight line 54. You would run A square bracket 2. And again, that would spit out the number 1. You could also type the same thing into the console and run it. Either way is totally fine. I told you that the length function basically tells you how long a vector is. So if I just in the console type length of A, whoa, what happens if you accidentally press tab? If I type length of A, it'll give me the number 5. That means there's 5 numbers in this vector. You can also see that if you look up in the environment, you can see that it's 5 is the bigger number here. That means it's 5 long. So if I wanted to pull out the last value of A, one way to do that is what you see in line 55, which is basically combining like 2 rows of code. The first is actually checking what the length of A is, and the second is putting that number in the square brackets to subset that number from the vector. So it'll tell you that the last value is 10, which you can see is true. As you go through, you're going to make a ton of variables and you're going to want to clean it up. The way to do that is through lines 58 through 60. So ls, this is a lowercase l, lists all the things in your environment. So if you type ls with round brackets, it'll show you the 4 things that exist in your environment. That's also the same thing you get from looking at the global environment in the top right corner. If you want to just remove one variable, you use rm. Rm is a function that just takes that thing and throws it away. So let's say we want to remove A, run line 59, and you can now see we only have 3 variables in our global environment. So you can go through and like delete one by one if you want. The thing that I do like every day that it's 5 o'clock and I'm like done programming is I just like clear everything. It's like a way that I just like start from scratch the following day. And the way to do that is to use this line here. So that basically says remove everything listed in the environment. And if I run that, you can now see the environment is empty. We have a blank slate to work with. That's a mistake I've seen a lot of people do, is not clear their environment when they go from working to one thing or another, like 2 different data figures, but you're working with 2 different data frames and they're both named data. And then you're accidentally plotting the old data instead of the new data. So I would just get in the habit of just like clearing your workspace, starting from scratch when you open a new source code. So that's kind of the simple stuff if you want to like build up from R. What we do most commonly is actually bring data in from spreadsheets. And we do that by working in a certain directory. So directory is basically a folder where you're working. You can pull files out of that directory and into R. You can put files from R into that directory. So as an example, let's say I have like, I don't know, 100 spreadsheets, each from an animal that's like tracking data, like GPS tracking data. I could actually go through file by file, pull them in from the directory to R, make some plot and then spit that plot back into the directory. So it's a really easy way to like manipulate files and make files in a really like in a batch, basically in a very like repetitive way that's really quick in R. So the most important thing is to set your directory. You can do this a lot of different ways. The probably most easy way is to go to session at the top, set working directory, and then choose your directory. And that'll just bring up like your files. So like these files are in on my desktop under basic intro to R, and then I can just open it. And if you look down at the console, you'll see R has created this line of code for me. It says set WD, which is set working directory, and then it's put together that path for me, which is really handy. So I could like copy and paste from this console into my source code, which I've already done. The alternative to that is you can actually go to Files in this bottom right panel, and you can navigate there yourself. So like I'll go to Desktop, and then I'll go Basic Intro to R, and then if you go to More on this right side, you can actually set as working directory, and you'll notice it wrote the same line of code for me. So different ways to do the same thing. People have different preferences. I always just check the working directory to make sure I didn't do something stupid. That makes me feel better. And I can see that the data set, for example, that I want to work with right now is in that working directory. Like that, there's two different ways to read in data. One is using read.csv. That's sort of the traditional method. So like if you work in Excel, you have an Excel file, which is a .xlsx extension. In Excel, you would do file save as, and you'd save it as a .csv. It's a comma separated value file. It loses its formatting, it loses its equations, which is fine if it's like a simple spreadsheet. If you do that and you have a CSV file that you want to load into R, this is the call that you use. So you do read.csv, and then you put the name of that CSV file in quotation marks. You have to set the data that you're reading in as something. So this line, if I run line 70, is going to take that CSV file, load it into R, and set it as something called D, which you can now see in my environment. And so if I want to look at that, I can just press this little arrow. This is what I showed you in the PowerPoint. You can see the different columns that there are. I can also just type D into the console, and I can just directly look at the data, which is kind of handy. That's totally a good way to do it. Another way to do it is to use this read_Excel function, and that way you can load Excel files directly in without saving them as a CSV first. There's pros and cons, but just know that both of those options exist. I'm just going to do this later one for now. And if you type in D, you can see that it's the same thing. We have these column names, and we have these different types of data in the different columns. Here are just some functions that I commonly use to check the data. Head views the top of the data. I think it's the first 5 rows or something. Yeah. Tail looks at the bottom of the data. So like sometimes in Excel, you may accidentally have like 100 blank rows of data on the bottom of your spreadsheet, and that'll mess up R. So I always run tail just to double check there's not a bunch of empty stuff. STR looks at the data structure, so you can check what it actually looks like. It's very similar to just using this little drop down in the environment. The number of rows is handy because it tells you how many rows there are. The number of columns tells you how many columns there are. And again, you can get those two numbers by just looking into your environment. Here there's 30 observations of 5 variables, which means there's 30 rows and 5 columns, which is what this just spit out here. And then if you want, you can make you can save your variable names. So if you just run call names D, just like this, it'll tell you what your column names are of your matrix or whatever you have. You can actually save them as var names, and that way they'll actually show up here in your global environment, and you can use those for lots of different things. That's really handy as well. We talked about how the $ subsets columns. So here, let's say I wanted to make a new column called total, and I wanted that just to be the mussel counts, the snail counts, and the barnacle counts all added together. So if you look at your column names, you know you have one called mussels, one called snails, and one called barnacles. So this line of code basically just says, take this data frame called D, the column called mussels, and then add that to the snail column and the barnacle column, and save that output as something called total. That's a column of the data frame D. Sorry, that's kind of complicated. But just know that if you run, for example, the second half of that code after the equal sign, it'll just do the math for you, but it won't actually save it. So then if I run that whole line, it'll do the math and save it. And now if we look at D in our environment, you see it has 6 columns, and that last column is called total, and it has the sum of the other 3 columns. We just talked about the $sign. There's different ways of doing this. You can subset something with the column name. So this is saying, give me the data frame D, but only the column that's called mussels. You can subset the third column. You can subset the first row. This is what we were talking about in the PowerPoint. So given time constraints, I probably won't do all of those, but just know that's how to subset, and you can play with those different things and just make sure that it's giving you the values you think it's going to give you. Tanya,
also, I don't think this got mentioned, but you can just click on the data frame in the environment, and it brings it up in a window in the scripts window, so you can just look at the table and make sure it's.
That's a good point.
What it's supposed to look like.
Depends how big your data frame is. But yeah, if you click on this letter D right here, then you'll see it pops up here.
If it's small, you can do that. If it's like giant, maybe not. So.
This is perfectly sized. Thank you for putting together such great example data.
It's not real, so yeah.
It's great. And then you either, so it pops up over your source code. So you can either click over to your source code, or you can just close it. I think the last sort of bigger thing is just, plotting and aggregation. So in plotting, Matt will go over this more possibly, but basically the syntax for doing a lot of stuff in R is y tilde x. So like if I should put that in the PowerPoint, good to know for next time. But here, let's say I want to plot snails on the y-axis and mussels on the x-axis. This is what that call looks like. So I say plot, and then I do y tilde x, and I have to specify that these are columns in the data frame D. So if I run that code, it'll pop up the data. You see snails are on the y-axis, mussels are on the x-axis. Here's the data. That's how you do it in BASE. This line 107, 108 is how you do it in ggplot. A little prettier.
So you can kind of think of the tilde as meaning as a function of, and that's how it's usually used in R. So y is a function of x.
Yeah.
So you can think of it that way.
Totally. And that is the call. It's the syntax for plotting. It's also the syntax for a lot of the statistics. So one thing I didn't say is R has a ton of functions for stats like t-test and ANOVA and all the stuff you can ever imagine. And a lot of those use this syntax, like on line 111 of y as a function of x or y tilde x. The linear model, like it's just a simple linear regression, is LM. And so you can see here that this is how you run a simple linear model and save the results as something called res. You can do that and then, for example, look at the summary of res, and that'll show you that, the intercept is 1.2 and the slope is 0.49. You can look at your error and your p-values and your r-squared values, all the things you would look at in like JMP or a different program, which is super handy. You can also do things like put, like overlay that linear model onto a plot using the AB line function, which just basically says put a line on the plot with that linear model. So you can begin to see how like saving these different things as variables can come in handy. We only have 5 minutes left, so I'm just going to very quickly go through the rest of the stuff. It's sort of more complicated, and you should be able to just go through line by line and see the different things. But if you need help with anything, just type help and parentheses and then put whatever the function is. So if you do like help of AB line, it'll pop up this help thing on the bottom right where your plot used to be, and you can just look through it and it'll tell you all the different things you need. And at the bottom, it usually puts some example code that's often really helpful. If you want to do a box plot, so if you have like one categorical variable, like tide height, we know is a category, you can see it's a character up here. You can run this line 117, which will do just a really simple box plot. So you can see, for example, how muscle abundance varies with tide height. I've also put the code for ggplot in there if you want to do a simple box plot, I think. Yes. And then aggregation and subsetting are the last like big thing. So aggregation is really handy if you want to be able to do something like here I aggregate the number of muscles, or I should say the variable muscles as a function of tide height with the function mean. So what this does is it takes the mean number of muscles per tide height. You could do length to count the numbers or whatever, but if I run this, you'll see it's going to spit out the two tide height options, which are high and low, and then the average number of muscles. So here we see that there are less muscles in the high tide treatment than the low tide treatment. And if you look at this box plot, I mean, you basically see the same thing. Aggregate is really nice. If you use a multiplication symbol between different like column names, so here this is saying, give me the average number of muscles at each combination of tide heights and sites, then it'll make something called means and it'll do that. So you can see here, there's site A, site B, and site C. Within each site, tide height is nested as either high or low. And then for each tide height and site combination, it calculated the average of muscles. So that becomes a really powerful tool when you have really large data sets. For subsetting, there's a function called subset. What it asks for first is that you put in the name of the data frame, then you put in whatever your specifications are. So this says, give me the part of the data frame D where tide height is equal to low and site is equal to A. And that'll literally just give you the low tide height at site A, and it'll give you the different counts that were done. Same thing if you wanted to say subset the data frame D where barnacles is less than 10, then you can do that same thing and it'll subset the data. So that's mostly what I wanted to get through. I'm gonna skip for loops, sorry Tanya. For loops are really important, but they're complicated and maybe best for a later time. But you all are welcome to go through the rest of the code and explore, and yeah, let me know if you have questions. We have 2 minutes if anyone has questions.
The one thing that wasn't mentioned, so at the beginning, there was some code for installing packages. So you only have to, so that code will download the package and store it on your computer. You only have to run that once, and then it's sort of forever on your hard drive. And then you just have to call it in the library function. So that's just how you would install packages. So some of these packages, like the reading Excel function is part of one of those packages that was loaded at the beginning. So that's just one more comment about that.
Yeah. Any other questions? Are you guys totally overwhelmed? I know it's a lot.
I thought that was really helpful. Sorry, go ahead, Miranda. I was just saying.
Sorry, Laura.
Guys.
I had a question of whether you, Tanya, and other people could put together some sort of handout that gives some tips on organizing your data for those of us that are just starting out. How would we, we want to have our load data first, and then and don't forget to put in your libraries, just to give us a visual of, here's a really great example of how Roxanne does the organization of some basic code and how Tanya does, since everyone does it differently. And it would just be really great for beginners to then start the organization really quickly.
Yeah, we could talk about doing that. It's sort of like everyone has their own style and comes up with their own way of doing things. And as my analyses have gotten more complex, I've started breaking things up a lot more and making it more modular. And so it's a little maybe more than someone doing more simpler analysis might need. But yeah, I can definitely talk about how I do things. And that could be a topic for future meetings.
I'm not saying that it necessarily has to be a complete topic, but if you just even had some example basic code of here's, and that it's focused on organization and hashtagging. Ugh.
Commenting, just call it a comment sign if you don't like the pound sign. Sorry about that, this is one of my pet peeves.
I think that's a great idea. I have never seen a lot of people's code, and so maybe what I do is totally weird. But one thing I was going to do for a Costa Lab meeting is give everyone the code and data sets for a paper that is coming out soon, so that everyone can recreate the figures that I made and see the code that went into organizing, uploading the data, aggregating the data, and then plotting the data. So I'm happy to share that with folks if that's helpful. Just know that I might do it weirdly.
What will next session be on?
Yeah, so just a reminder, and I'll send out a follow-up email that for now on, the meetings are going to be from 11 to 12, and I'll set a reoccurring Zoom meeting, which is going to be different from this one, just that's at 11 to 12. And then I think next week I'll be, so the way we're doing it, if it wasn't clear, if you can go in the schedule, let me share my screen.
Yeah, so I think we're gonna alternate between more advanced topics and beginner topics. So I think next week, yeah, so Matt's gonna talk about running R on a supercomputer. And then the week after that though is basic plotting in ggplot. So that'd be another one for beginners to come to. So, and then I'm gonna talk about functional programming, so.
And also, if you are a beginner, you can totally come to some of the specialized topics. Just especially for apply family, I think once we, I think that's something that people could come to.
It's an seemingly esoteric topic that's actually really useful. So.
Are there any other questions?
All right, I gotta go to another meeting, so I'm gonna leave now, but let me know if you have other questions.
Thank you.
Thank you. Bye.
Bye.